Hello and welcome to Module GL301, Basic Drilling and Well Completion Technology, the first module in our series on well site geology. In this module, we will introduce the equipment and procedures involved in drilling wells and also in preparing wells for production or completing them. First, we shall outline the wide range of environmental conditions that are encountered by a modern drilling operation. We shall explain the types of drilling equipment used to manage these conditions, surface conditions like wind and water, and subsurface conditions like pressure and temperature. After we have established the basic components of the drilling system that are present in every type of drilling operation, we shall follow the drilling of a well from beginning to end. The differences between onshore and offshore drilling equipment will be highlighted. After our well is drilled, we can then spend some time discussing the procedures followed in the completion process.
A modern drilling operation, or rotary drilling as it is called, has its roots in percussion drilling, performed by cable tool rigs. Thousands of years ago, the Chinese were using similar equipment to alternately raise and drop a heavy metal bit, slowly beating a hole into the earth in their search for sources of salt. The procedure was still being followed for drilling water wells when Edwin Drake first applied it to the search for oil in Pennsylvania in 1859. In the meantime, however, inventors in Europe had been developing techniques for boring into the earth and flushing the rock particles out of the hole with water. They began using their equipment to drill for oil, and the practice spread to the United States, where in 1901, a Yugoslavian immigrant named Anthony Lucas used rotary equipment to drill the gusher that discovered the Spindletop field. By 1930, the success of the rotary drilling technique had firmly established it as the chief method for making coal in an increasingly oil-hungry world. The expanding search for oil has required drillers to explore in areas much less hospitable than Colonel Drake's western Pennsylvania hills or Lucas's Texas prairie. Today, drilling technology must adapt to rugged mountainous terrain and tropical jungles. A vast amount of the world's oil is located in the deserts of the Middle East and the ice-choked waters of Alaska's North Slope. One of the most violent, storm-tossed oceans of the world, the North Sea, is also the source of over 20 billion barrels, 3 billion cubic meters, of oil reserves. Offshore drilling equipment must be adaptable to the water and the weather, as exploration for new fields extends into greater ocean depths. But drilling operations must deal with not only the conditions at the surface of the earth, but also with conditions in the subsurface, where hopefully the bit is steadily drilling deeper and deeper. In general, along with this increasing depth comes increasing pressure, and controlling the pressure of the subsurface environment is a major part of the drilling operation. Let us consider subsurface pressure for a moment. Most of the sediment in the sedimentary basins in which drilling is conducted was deposited along with or later invaded by water. Therefore, the porous rocks of the petroleum reservoir and the formations above it all contain water. The fluid pressure in the pores of these water-filled rocks increases with depth, just as it would in any body of water, whether an ocean or a swimming pool. The reservoir pore pressure at a particular depth is a result of this fluid column reaching toward the surface. The rate of pressure increase, or pore pressure gradient, depends on the density of the water, and the water density depends primarily on the amount of dissolved mineral salts, that is, the salinity of the water. Of course, the load of sediment above a reservoir also exerts pressure. If we add together the pressure exerted by a column of sediment and the pressure exerted by the column of water within the sediment, we have what is called the overburden pressure. Overburden pressure increases at a rate of about 1.0 psi per foot, or 23 kilopascals per meter. About half of this increase is due to the fluid and half to the sediment. Certain geological or geochemical processes can affect the pressure gradient, causing it to deviate from its normal trend and account for a larger portion of the overburden pressure. This can happen during the rapid deposition of sediment in a basin. As sands and muds are buried deeper, the water squeezed out of the compacting mud may escape through the permeable sands. However, some water trapped in the sands has no way to escape and therefore must help carry the load of the sediment above. Consequently, the fluid pressure in the porous sandstone surrounded by shales is higher than expected. If the pressure exerted by the column of fluid in the borehole is substantially less than this unexpected pore pressure, the formation fluids in the permeable rock will flow from high to low pressure, a potentially dangerous situation. Another factor contributing to the hostility of the subsurface environment is temperature, which also increases with depth, usually about 2 degrees Fahrenheit per 100 feet, or 3.6 degrees centigrade per 100 meters. High temperatures require expensive, specially formulated drilling fluids and can seriously affect the performance of downhole equipment, weakening metal parts and causing electronics to malfunction. And of course, the rocks themselves can make things unpleasant. Gumbo shales which stick to the drill pipe and plug bits, salt formations which ruin costly drilling fluids, and high permeability rocks which steal the drilling fluid from the hole. But drilling systems have been developed to meet the challenges of both the surface and the subsurface environments. The variety of drilling rigs includes onshore and offshore types. This onshore rig has a derrick or mast designed to allow assembly on the ground prior to being hoisted into position by the rig's own power. Some smaller land rigs are permanently attached to a truck for increased mobility. Offshore drilling rigs fall into one of several categories, each designed to suit a certain type of offshore environment, primarily water depth. The barge rig is a flat-bottomed vessel which can be towed to a drilling location and ballasted to rest on the bottom of a shallow lake or swamp. A submersible rig is a larger version of this type, capable of maintaining stability for work in deeper waters. Self-elevating or jack-up rigs are designed to float to a drilling location with their legs in the air, at which point the legs are jacked down to the sea floor, lifting the drilling deck above the waves. Rather than resting on the seafloor, semi-submersible drilling rigs are in a different class of offshore vessels. They float. The drilling deck on a semi is supported by submerged pontoons and kept stationary by anchors or sophisticated computer-controlled propellers. Their ability to float makes these rigs capable of drilling in water depths of several thousand feet. Another type of floater is the drill ship, a self-propelled vessel with a hole through its midsection and a derrick above. A drill ship is capable of storing large amounts of drilling materials and therefore operating for long periods at remote locations. Offshore drilling is also undertaken from permanent drilling and production platforms. On these structures, which are fixed to the seafloor, the drilling derrick may be moved to different positions in a pattern until 4, 8, 12, or perhaps 20 wells have been drilled and completed from the single platform. Each of these drilling rigs, despite variations for a particular environment, still provides the means to perform the 4 basic drilling functions. In this respect, all drilling rigs are alike and really haven't changed much from the early rotary rigs. The 4 drilling functions are hoisting, rotating, circulating, and controlling. Each function is performed by several components, all of which fit together into a smoothly operating system for making whole. Hoisting is accomplished by the crown block, the derrick or mast, the traveling block, the hook, and the drawworks. The derrick sits upon the substructure and permits vertical movement of the suspended drilling apparatus, and also the occasional removal of the string of pipe from the hole. The drawworks is a spool or drum upon which the heavy steel drilling line is wrapped. From the drawworks, the line is threaded through the crown block at the top of the derrick and through the traveling block, which hangs suspended in the derrick. By reeling in or letting out drill line from the drawworks, the traveling block and suspended drill pipe can be raised or lowered. Attached to the traveling block is the hook, which is used to latch onto the drilling apparatus necessary to accomplish the rotating function of the drilling system. The components of the drilling rig involved in rotation are the swivel, the Kelly bushing, and the rotary table. The swivel allows the suspended drill stem to rotate while supporting its weight and providing a pressure-tight connection for the circulation of drilling fluid. Connected to the swivel is the Kelly, a multi-sided length of hollow steel which is used to transmit the rotational motion of the rotary table to the drill stem. The flat-sided Kelly fits through a corresponding opening in the Kelly bushing, which in turn fits into the spinning rotary table turned by the rig's power source. In this manner, the rotary motion required to turn the bit is transferred to the drill stem. The circulation system includes the return line, solids control equipment, the mud pumps, and standpipe. Circulating is required in rotary drilling to carry rock cuttings out of the hole and cool the bit. The mud pumps are the heart of this system. Their pistons suck the mud from the pits and discharge it to the standpipe, where the mud rises up past the drilling floor and enters the rotary or Kelly hose connected to the swivel. The circulating mud moves through the swivel, Kelly, and drill pipe, exiting through the bit at the bottom of the hole. From here, the mud moves up the annular space between pipe and hole, carrying the drilled rock cuttings in suspension. At the surface, the mud leaves the hole through the return line and falls over a vibrating screen called the shale shaker. This device screens out the cuttings, allowing them to be sampled before being discarded. Cleaned of large cuttings, the mud may then be sent to a degasser, where small amounts of gas picked up from subsurface formations are removed. Desanders, desilters, and a centrifuge all employ centrifugal force to remove progressively finer particles from the mud. With all these solid particles removed, the mud is now ready to repeat its journey through the system, starting again at the pumps. Controlling subsurface pressure is the fourth basic function of the drilling system and is accomplished through the use of the accumulator, blowout preventers, and choke manifold. Although the drilling fluid is used to maintain hydrostatic pressure on the formations encountered by the drill bit, when the well unexpectedly kicks and subsurface flow occurs, the blowout prevention equipment is needed. Blowout preventers are a series of powerful sealing elements designed to close off the annular space between the pipe and hole, where the mud is normally returning to the surface. The BOP stack consists of an annular preventer, a donut-like rubber ring which may be hydraulically squeezed to conform tightly to the drill pipe in the hole, pipe rams which contain rubber-lined steel jaws designed to grip the drill pipe, blind rams designed to close off the hole after the pipe has been removed, or shear rams designed to actually crimp the pipe in two, sealing the hole in an emergency. Blowout preventers are opened and closed by hydraulic fluid stored in an accumulator and controlled from either the accumulator itself or a control panel on the rig floor. Once a kicking well has been shut in with the BOPs, the high-pressure formation fluid must be circulated out of the hole and the mud system adjusted to contain the pressure before drilling further. The circulating mud is detoured from the closed-off annulus below the BOPs to a choke manifold, where it is passed through a choke or adjustable valve controlled from a remote panel. By carefully adjusting the size of the choke opening, the drilling engineer can maintain the pressure in the annulus required to prevent further kicks until the well is balanced once again. The equipment used for hoisting, rotating, and circulating is supplied with power from the rig's prime power source, usually diesel engines. Most modern rigs use the engines to drive electric generators, which produce electricity that is sent through cables to a switch and control house and then on to each end user. Hoisting, rotating, circulating, and controlling pressure are functions performed by every rotary rig. Two of the drilling system's components, which we've mentioned already, are critical in the performance of these four functions and require a closer look. They are the drill stem and the drilling fluid. The drill stem includes the kelly, the drill string, and the bit. The drill string is made up of lengths of steel pipe, drill pipe, to which are welded threaded pin and box ends. Similar to drill pipe, but having larger outside diameters and smaller inside diameters, are joints of pipe called drill collars. The heavy drill collars are used at the bottom of the drill string to hold the pipe in tension and prevent it from buckling, a problem which doesn't seem possible when looking at these pipe joints stacked here, but imagine them joined together to form a flexible string, a mile or two long, dangling down the borehole. If we try to put weight on the bit from the surface, the string will buckle. But by adding the weight on the bottom with the drill collars, a pendulum effect keeps the pipe in tension while we drill ahead. Other important components of the drill string included near the bottom are stabilizers, used to keep the pipe centered in the hole, and a variety of shorter length components, or subs, described in your manual. Perhaps the most important part of the drill stem is the component where the real action is taking place, the bit. Drill bits have evolved into precision machined mechanisms with a wide variety of designs to match the variety of rock formations and drilling conditions they encounter. The three-cone rolling cutter bit is the most commonly used bit today. The cones mesh together to provide a self-cleaning action, which is furthered by the directed flow of drilling mud from the three nozzles or jets through which the drilling fluid is pumped at high velocity. The teeth bite into the rock, gouging and scraping away the cuttings, which are carried to the surface by the circulating fluid. Rolling cutter bits are distinguished by the type of teeth used, either milled tooth or tungsten inserts, and by the bearings used to attach the cones to the bit body. Non-sealed bearings that are internally lubricated by the drilling fluid, sealed bearings that are lubricated by an internal grease reservoir, or journal bearings, where a precision-machined hard alloy surface replaces the cylindrical roller bearings. Diamond bits do not have cones, but rely on industrial diamonds embedded in a hard steel matrix to crack and abrade away the formation. Although diamond bits are much more expensive than roller cone bits, they can be economical on a cost-per-foot basis, especially in deep wells with hard rock formations. Whatever type of bit is used, all bits perform their job with the help of the drilling fluid, which cools the cutting surfaces and circulates rock chips uphole from the bottom. Like the technology behind drill bits, drilling fluid technology has become increasingly sophisticated. In most cases, the circulating fluid utilized in a rotary drilling operation is a water-based mixture of clays, suspended solids, and chemical additives, appropriately called mud. In some cases, oil is added to the fluid, or the entire system may be converted to an oil-based rather than a water-based mixture. In any case, the drilling fluid must have properties which enable it to control subsurface pressures, remove cuttings from the hole, cool and lubricate the drill stem, and aid formation evaluation and productivity. Let's look at each of these functions. The drilling fluid controls pressure, as we've already mentioned, by imposing hydrostatic pressure against permeable formations and preventing flow. The natural density of the drilling mud being measured here with a mud balance can be increased by additives such as barite, a mineral with a high specific gravity. But wait a second. If the pressure exerted by the drilling mud is great enough to prevent flow from the permeable formation, how do we prevent flow into the formation? Good question. One of the properties of a drilling mud is the ability to form a filter cake of clay particles on the wall of the hole. As the hydrostatic pressure of the mud column causes flow into a permeable formation, the clay particles screen out on the wellbore wall, eventually forming a seal and preventing further fluid loss. If, however, an extremely permeable formation is encountered, or if the pressure of the drilling fluid is sufficient to fracture the rock, lost circulation can occur. and the fluid pumped down into the drill pipe disappears into the rock formation, decreasing the amount of mud in the hole and setting the stage for a kick or even a blowout. In such situations, lost circulation material must be added to the drilling fluid to enhance its filter cake forming ability and stop the loss of mud. The viscosity of the drilling mud, being measured here with a Marsh funnel, is the property which helps it carry cuttings up and out of the hole as it is pumped through the circulation system. A drilling fluid must have gel strength to hold the cuttings in suspension should pumping stop, and yet must quickly liquefy when pumping begins again. Cooling the bit is also an important function, especially considering the heat which can be generated by the forces applied to the rapidly spinning bit, and the subsurface temperatures which increase with depth. In addition, the drilling fluid must also be formulated to avoid damaging the ability of the petroleum-bearing formations to produce. Formation damage occurs when the drilling fluid reacts with natural clays in the formation, causing them to expand and block the passageways for oil flow. Additionally, the mud must not inhibit formation evaluation by electrical, acoustic, or radioactive methods. The trade-offs involved in designing an efficient mud system must be decided by engineers and geologists together to ensure that the well is drilled safely and economically, and that the maximum amount of geological information is acquired.
Hoisting, rotating, circulating, and controlling subsurface pressures. These are the functions which every rotary drilling rig performs, regardless of how it has been adapted to work in a particular environment. Now that you have a basic understanding of the equipment used in performing these functions, our next step will be to travel to our own well location and follow the drilling engineer through a step-by-step close-up view of the drilling process. But first, let's take some time to review what you have learned so far. Please work exercises 1 through 3 in your manual. Now it's time to get a first-hand look at how a well is drilled, what happens when and why. Let's start at the beginning with the preliminary paperwork, and then we'll go out to the drill site and follow our well's progress from start to finish with the help of the drilling engineer on location.
Based on a detailed geological study which may involve seismic surveys and extensive mapping of subsurface data from previously drilled wells, the geologist writes a well proposal giving the exact location of the prospect and the expected productive formations. Only after the company's land representatives have obtained all the necessary leases from the landowners and all the required permits have been filed with the proper governmental authorities can work begin. Based on the geologist's well proposal, the next step in most companies is the preparation of a detailed drilling program and cost estimate. This plan is based on the past performance of drilling operations in the same or similar areas and the current cost of drilling services and materials. The exact requirements of the program, including depth, commencement date, formations to be encountered, hole size, casing sizes and setting depths, logging operations, testing and completion programs, all are necessary for the negotiation of a contract between the operating company, usually an exploration and production company, and the drilling contractor, the company providing the rig and drilling personnel to drill the well. Often when a well is being drilled by a group of partners as a joint venture, a detailed cost estimate and list of drilling objectives are included in an authorization for expenditure, or AFE, which is signed by each of the parties involved, authorizing the operating company to proceed with drilling.
With all the preliminary paperwork out of the way, the process of making hole finally gets underway. Of course, that's not to say that there won't be any more paperwork. Keeping careful, accurate records is an important part of any drilling operation. At most land locations, such as this one, the location is first surveyed, and then the location is staked to make sure that the well is drilled exactly where it should be. Offshore, satellite navigational aids are often used to locate rigs very precisely. even though there are no county roads or lease roads to act as landmarks. Next, leveling may be required, and often the whole location will be covered with wooden planks in a swampy area, or crushed rock or caliche such as we have here, to prevent mud from being a problem for the heavy equipment that is brought in. The reserve mud pit is excavated and lined with plastic to prevent runoff, and the entire location is surrounded by a drainage ditch. At the staked well location, a cellar is dug to accommodate the components of the surface equipment, which will be below ground level when the well is completed. A conductor hole is started in the center of the cellar and lined with a conductor pipe. This first portion of the hole may be started with a portable spudding rig or by the drilling rig itself. The rig is brought to the location. Out here, there's no problem bringing it in on trucks, and the substructure is erected next. The components of the mast are fitted together, and the entire assembly is hoisted upright using the drawworks. All of the other rig systems must be arranged around the location, and any necessary piping, electrical connections, water lines, and compressed air hookups are installed. This entire process can take several days or even longer, depending on the size of the rig, the remoteness of the location, and the complexity of the procedures planned for in the drilling program. We're all rigged up and ready to go. This location took 50 truckloads in 2 days. But before we start drilling, let's introduce a few of the personalities involved in this particular operation. The tool pusher is the drilling contractor's senior representative on location. The pusher directs the drilling crew and the maintenance of the rig and its equipment. Reporting to the tool pusher is the driller, an experienced hand who operates the drawworks and rotary table and directs the drilling crew on the floor. This crew includes the derrick man, who works high above the drill floor, guiding pipe as it is moved in the derrick while running in or out of the hole, and the roughnecks, who handle the lower end of the drill pipe using the tongs to make up or break out the tool joints. Roustabouts maintain equipment and do general housekeeping. All of these folks usually work for the drilling contractor. The operating company that has engaged the drilling contractor usually has a representative on location to make sure the operation runs safely and efficiently, and to make on-the-spot decisions relating to the drilling program. That's me. I stay in close contact with my supervisor back at the office, but spend most of my time right here, keeping an eye on things. I'm also responsible for ordering out other contracted personnel needed to perform special services such as running casing, cementing, logging, and so on. I'll also be working very closely with the well site geologist responsible for this well. On exploratory wells, the well site geologist will play a very important role from the very beginning, and he'll be out here quite a bit of the time gathering every bit of useful data that's available on the well. On a development well like this one, the role of the well site geologist becomes increasingly important as we near our objective. The input from the well site geologist on casing points, logging operations, and test data is very important, especially concerning the completion decisions surrounding the well. Well, now that we're all acquainted, let's get down to work. Our drilling program has been designed so that the initial bit will drill a hole large enough for casing that can accommodate successively smaller bits and casing strings. The number of casing strings required to safely reach our target depth will determine the initial hole size. Attached to the first large bit are the first drill collars. Weight is applied by the driller, slacking off on the brake. The driller then starts the rotary table turning, which turns the Kelly and transfers the torque to the drill stem. As the bit chews away at the bottom of the hole, the driller slowly lets the Kelly move downward, deeper into the hole, maintaining the correct weight on the bit. While the driller is watching the Kelly and the weight indicator, the circulation system is doing its job. Then we see the mud pumps displacing the mud from the pits up into the standpipe, through the rotary and swivel, and on down the drill pipe. When the mud has completed its journey to the bottom of the hole and exited through the nozzles in the bit, it returns up the annulus, carrying the rock cuttings with it, and exits the wellbore through the return line, leading to the shale shaker and on to the mud cleaning equipment. Looks like they're about ready to make a connection. Let's go take a look. Each time the length of the Kelly has been drilled, about 30 to 40 feet, or 9 to 12 meters, another joint of pipe must be added to the drill string. Here's where the roughnecks get busy. First, a new joint of pipe is hauled up through the V-door and lowered into the mouse hole, with its box end up. They then wait for the driller to lift the Kelly and Kelly bushing, exposing the pipe joint connected to the bottom of the Kelly. Then they quickly set the slips, whose teeth grip the pipe and allow the drill string to hang in the rotary table. Now the Kelly can be disconnected using the tongs to first break the joint. Next, the Kelly is swung over to the pipe waiting in the mouse hole, and its pin is stabbed into the box and tightened up. The driller can now pick up the new joint and swing it over the pipe waiting in the slips. Here it is connected, once again using the tongs to tighten this time instead of loosen. With the new joint now a part of the string, the pipe is picked up, the slips removed, and the drill string lowered back to bottom, now one joint longer. When the Kelly bushing fits into the rotary table, the process of drilling down the Kelly starts once more. Each time a connection is made, there's an indication here on the depth and drill rate recorder, which is usually located in the doghouse near the drill floor. This device monitors the position of the Kelly as a function of time on a continuously recording chart. This allows the driller or the engineer or the well site geologist to determine the rate in feet per hour that the well is being drilled. There are a few other important things here in the doghouse. For example, this is the daily drilling report form that's kept current by the driller or the tool pusher. It's a complete log of all the activities that occur on the rig and the times at which they occur. It also includes important things like the measurements of downhole equipment, the mud viscosity and mud weight, the bits run, the type of bit and when, and notations of important safety drills. Things have been going smoothly while we drilled our surface hole. They're just about ready now to pull out of the hole and run casing. I'll meet you folks up on the drill floor and we can see how they handle the pipe during a trip. When tripping into or out of the hole, the pipe is handled in stands, usually 2 or 3 joints each. First, the slips are set and the Kelly is disconnected, and the Kelly, rotary bushing, and swivel are stowed in the rat hole. With the Kelly unlatched from the hook, the elevators, which hang from the hook, can be latched around the pipe just below the tool joint. They can then be used to lift the pipe out of the hole. When several joints have been lifted up into the derrick, the slips are used once again to hang the drill string, while the bottom tool joint is broken with the tongs and unscrewed. The stand of pipe is then swung to one side of the drill floor, where it is set down and secured at the top by the derrick man. The hook and elevators are lowered once again, and the process is repeated, very smoothly and efficiently, until all the pipe is racked in the derrick. Tripping can take many hours in a deep hole, and time is money, particularly on a drilling rig. We don't want to make any unnecessary trips, so we try to drill as far as we can with a bit before pulling it, or as deep as we safely can before setting casing. Of course, if we push our luck too far, an overworked bit could drop a cone, or trying to drill a long open hole section just a few feet further before setting casing could result in stuck pipe. Part of the job of the drilling engineer is to avoid these types of problems while drilling the hole as safely and efficiently as possible. They'll be busy for a while. Meanwhile, let's take a look at the equipment involved in running and cementing the casing after the pipe is out of the hole. When the casing is delivered to the location, especially smaller diameter casing, it is usually rabbeted. That is, each joint has its inside diameter checked to make sure that tools which are run into the casing after it is in the ground will not get stuck. On the bottom of our first joint of casing, we'll run this guide shoe. It's shown here upside down, but we'll be running it in this end first. It has a rounded nose to facilitate movement of the casing string all the way down the open hole. Around several joints of the casing, we'll also be running these centralizers. The centralizers keep the string centered in the center of the hole and allow the cement to move evenly around the outside of the casing between the casing and the open hole. We'll also be running this baffle plate about one joint above the casing shoe. The baffle plate allows us to pump a rubber plug down the inside of the casing behind the cement and allows that plug to seat on this baffle plate and provide a means of telling us when we've displaced all of our cement out the guide shoe and around the outside of the casing. After we run our large diameter surface casing, we'll be running a smaller diameter, in this case 9 5/8 inch casing, inside of it. We'll also have a guide shoe on the bottom of our 9 5/8 inch casing that'll act just like the guide shoe on the surface casing. A float collar placed several casing lengths above the shoe contains a one-way valve which allows the cement to be pumped down the casing but does not allow drilling fluid or cement to flow back up inside the casing. After all the casing has been run into the hole, the cementing procedure can vary in its complexity depending on the depth of the hole and the number of cementing stages required to fill the space between the hole and the casing with cement. The cement is mixed and pumped from a truck like this one, or in offshore situations from a special pumping system including on the drilling rig itself. The cement is pumped through a cementing head attached to the casing at the surface, on down the inside of the casing, and up the annulus between the casing and the hole. The displaced drilling mud can be seen flowing out at the surface. Plugs, such as these, are dropped into the casing both before and after the cement slurry is pumped to isolate it from the drilling fluid ahead and the displacing fluid behind. When the second plug hits bottom, the pump pressure tells us that the cement has been correctly placed around the casing. With the casing securely cemented in place, the hole can be safely deepened without fear of losing circulation into shallow, low-pressured formations. As drilling continues, successive casing strings will be run and cemented concentrically to isolate and protect each open hole interval. After the hole is deepened from the surface casing, an intermediate string may be necessary, possibly followed by a liner string. A liner string being one that is hung from the inside of the previous casing string and extending downward into the open hole, but not necessarily tied back to the surface. Finally, production casing will be run to bottom, but only after the well's objective formation has been reached and evaluated as productive. But we still have some hole to drill before we reach our objective, and as we drill deeper, things can get a bit more difficult. For example, fishing. Now, I like to go fishing just as much as the next person, so long as it's for striped bass in a pond, and not for 1,000 feet of drill pipe stuck in a 10,000-foot hole. Stuck pipe is something that can result from a number of situations. Common problems include differential sticking, when the pipe comes in contact with a permeable formation and the string is sucked against the side of the hole and held by the pressure differential between the mud column and the formation. Another problem that can occur is key seating, where a crooked hole causes the drill pipe to wear a slot in the wall of the hole, which can stick drill collars when they're pulled out. or sloughing shale or too much mud cake on the walls of the hole, which can also stick the pipe in the same manner. In any of these situations, the pipe may have to be purposefully parted or unscrewed downhole so that fishing tools can be used to pull out what's left in the hole, the fish. Sometimes the pipe breaks on its own from metal fatigue, or foreign objects like the cone from an overworked bit, such as you see right here, can also drop off and get lost in the hole, and these must be retrieved before drilling can continue. A wide variety of fishing tools are used to retrieve these objects, depending on what is lost and how the fish is positioned in the hole. Some of these are shown in your manual. Another problem that we run into as we drill deeper is pressure and keeping it where it belongs, underground. As we mentioned earlier, formation pressure results from a fluid pressure gradient, which is offset and controlled by the pressure of the column of drilling fluid in the hole. But if we drill into a permeable formation, which has a higher pore pressure than we expected, we can take a kick. That is, a flow of formation fluid into the wellbore. A kick can also occur anytime the column of mud in the hole, and therefore the hydrostatic pressure, drops enough to permit a downhole formation to flow. For example, when we pull pipe out of the hole and forget to replace its volume with mud, or when the mud weight is sufficient to cause flow of whole mud into a subsurface formation. When we take a kick, the pressure control function of the drilling rig comes into play. When a volume of formation fluid, say gas, flows into the wellbore, it will rise in the hole due to its low density relative to that of the mud, just like air bubbles underwater. As it rises, it pushes mud out the return line, even when the pumps are shut off, and that's a sure sign that we're taking a kick. As it pushes the mud out, the pressure exerted by the mud column on the bubble decreases, allowing the bubble of gas to expand and push more mud out of the hole, which can allow more formation fluid to enter the wellbore, which can lead to a blowout. So it's very important to keep the formation flow, the kick as we call it, from rising in the annulus. And we do this by shutting off the annulus with the blowout preventers, using the annular preventers or the pipe rams. The blowout preventers are operated from a panel close to the driller's console on the drill floor. The driller keeps track of the mud pit level to be sure and to be on the lookout for kicks. Now that we have this bubble of high-pressure gas sitting at the bottom of the hole, we've shut in our preventers, we've kept it down there, what are we going to do with it? Well, if we leave it alone, its low density will still let it slip up through the mud, even though the well is shut in. Except the bubble of gas will not be able to expand, it won't be able to push mud out, and so a high-pressure bubble at the bottom of the hole will still be a high-pressure bubble of gas at the top of the hole. This high-pressure gas at the surface could increase the pressure on the mud column enough to break down a weak formation, causing lost circulation and possibly an underground blowout. Or the high-pressure gas at the surface could also exceed the pressure limitations on our surface equipment, causing a surface blowout. So we must circulate the kick out of the hole by putting heavy mud down the drill pipe and pushing the bubble of gas slowly up the annulus and out through an adjustable valve or a choke. We control the choke from a choke control panel on the drill floor, enlarging the choke or narrowing the choke in order to keep the kick circulating, but at the same time prevent the pressure from dropping enough to permit more formation flow. When the pressurized gas bubble finally gets to the surface, we'll divert it out one of these flare lines to the pit. And believe me, you'll know when it gets there, it can sound like a jet airplane engine. Now all that sounds a bit simpler than it really is. In fact, the engineer on location needs to be constantly aware of all the information needed to perform the calculations necessary to do what we just described. All the planning and thinking needs to be done in advance because there may not be much time to waste after the kick occurs. We still have quite a bit of hole left to drill before we reach our TD. Let me check in with my drilling supervisor and call in my daily report. Back at the office, our progress has been plotted on a depth versus time plot in order to compare our actual drilling performance with the proposed drilling program. Every day I call in a report of the latest 24 hours activities, and these daily morning reports will ultimately end up as part of the well's permanent file.
As our drilling target gets closer, preparations for the evaluation of the potentially productive formation will begin. The mudlogger has been keeping a lithological log of the hole based on the cutting samples caught at the shale shaker and analyzed on location. This information is helpful to the geologist in anticipating the depth at which our objective will be met. When total depth is reached, a variety of logging devices can be lowered into the hole to record the properties of the penetrated rocks and evaluate the productive potential of the formations. We may also sample the rock formations with a sidewall sampler, which punches thumb-sized plugs of rock from the sides of the hole, or a repeat formation tester, which allows a sample of formation fluid to be retrieved at one or more points in the hole. If we need more information to determine if our well merits completion, we can go one step further and cut a conventional core by stopping drilling just before the anticipated producing zone and replacing the bit with a core bit and barrel, which cuts a cylindrical core of rock from the formation and allows us to view it directly at the surface. We might also carry out a drill stem test, where we temporarily isolate the productive zone and allow it to flow, letting us see firsthand its productive capacity and fluid contents. All of these evaluation techniques allow the geologist and engineer to determine the productive potential of the well. Knowing which formations will produce and how much oil or gas can be expected is critical to the decision as to whether the well should be completed or abandoned.
While drilling continues on our well and the geologists decide what sort of logs to run, let's talk a little bit about the differences between land rigs, such as the one you've seen here, and offshore drilling rigs. Any offshore drilling can be difficult because of space limitations and the problems of transporting people and supplies in all kinds of weather. But drilling from floating drilling rigs, like a semi-submersible or a drill ship, has some unique problems, including maintaining position over the drilling location, providing a connection between the BOP stack and the drilling floor, operating a BOP stack on the seafloor, and compensating for the up and down movement of the drilling vessel.
Maintaining position over the well location can be accomplished by anchors and mooring lines, deployed in a pattern which minimizes vessel movement under the prevailing current and wind conditions. Dynamic positioning, on the other hand, involves the use of computer-controlled propellers, positioned to exert thrust and counteract wind and wave forces. Acoustic sensors on the seafloor are used to monitor a vessel's movement and inform the computer when to activate a thruster and adjust position. Handling the problem of distance from the drill floor to the seafloor involves a system with several very technologically sophisticated components, including the subsea BOP stack, which is lowered down to the seafloor along guidelines and connected to a guide base previously placed on bottom. A flex joint, which is a pressurized ball joint allowing about 10 degrees of angular deviation. The riser, which is a large diameter pipe serving as a conduit for the drill pipe and mud returns. A slip joint, which is a telescoping link between the upper end of the riser and the drilling vessel. The riser tensioner, which prevents the riser from bending or sagging. And flexible control lines, which allow the subsea BOP stack to be controlled from the surface. Above the drill floor, a drill string motion compensator is used to automatically adjust the block position and maintain a constant weight on the bit. With all these systems in place, the floater can indeed float up and down, while the drill stem remains in the same position relative to the borehole, just as it would on land.
Because offshore wells are expensive, a major means of cutting costs is to put all the wellheads on one platform, where they can be serviced together. Obviously, in order for the wells to drain a large reservoir, their bottom hole locations must be widely spaced, and this requires that the wells be drilled directionally. Directional wells are also drilled on land anytime we wish the bottom hole location of the well to be somewhere other than underneath the rig. Directional drilling involves kicking the well off or deviating it from a straight down path and then maintaining that direction to the final target, adjusting course along the way.
One method of deviating a well uses a bent sub to position the bit to point in the direction required. Downhole motors use a turbine powered by the circulating drilling mud to turn the bit. Jet bits are also used to wash away one side of the hole with high-velocity drilling mud and create a new avenue for the bit to follow. While another technique uses a whipstock, a long inverted concave steel wedge which deflects the drill string toward one side of the hole.
Of course, once our hole is deviated, we need to know where it is going so that we can adjust our drilling parameters and equipment to direct it towards the target. We also need to be sure that straight holes are where they're supposed to be. Both the inclination and the direction of a well bore are obtained with a magnetic survey device. This tool is run inside the drill pipe on a wire line when the drill string is stationary. And a built-in timer actuates a camera which records a compass bearing at the bottom of the hole. When the tool is retrieved, the reading can be plotted on a graph which shows the path of the deviated well.
Well, we made it to our target depth with a minimum of problems. While our friend prepares for the logging operation, please take a moment to review the material we've covered and work exercises 4 and 5 in your manual.